What's up?
All right, hey everyone. So what I handed back to you is at least lab 3 and your calculations. And so you should have all the grades that you have for this module, and you know what you need in order to make a C on the exam for this module, right? The C's get degrees. Anyhow, you should have all your grades, right? Okay? And so kind of the thing is it's kind of cumbersome for me because some of y'all turned that in by paper, some of you turned it in through email. So I had to download each one of those and print the labs off because I can't write on that picture. I'm fine with that, that's perfectly cool. If you turned your calculation in through iLearn, your feedback and your points minus and your, here and there, and you can look on that and see, that can be kind of cumbersome for me. I don't mind doing it, but it can be cumbersome. So then yours, like your feedback is in iLearn. Go check that out, your scores are there. And if you've got a paperback that you turned in, I made those notations and feedback and kind of what I was looking for on that. Everyone seemed to do fairly well. I guess the thing I should have stressed a little bit more was this exercise was more about the thoroughness of your work than it was so about the math. I mean, we're doing multiplication and division, right? This is basic math. So I wasn't testing your math skills per se. I was really checking to see how thorough you were. And as I was doing this, and I was noticing that there were some people who put every single unit, they showed their work perfectly clean all the way through, and then some of us were just the numbers. And I used to be a just the numbers guy, okay? And I hated having to write out all of my units. It just drove me nuts. Like, I'm too quick with math. I don't have time for units. What it comes down to is that the person who turns in the thorough work with all the units, they're the person that gets the job. So, like, when you're thorough, your boss doesn't have to worry about you. They know they can count on your work consistently, and they know that it's going to be thorough. And so, I didn't take off too many points, but if you had points taken off, it was because we were missing a couple of those units. Those units are important. Y'all, I hated it too. My bosses and my professors, they counted me off for every little single thing, man. I hated it. But, like, on the other side of the fence, on the other side of graduation, I understand why it's so important. Like, it really is. Y'all are smart. Your math is on point. Maybe question 9 tripped a few people up, but other than that, y'all nailed it. It's the thoroughness and putting in each unit and making sure that the calculation is clean all the way through to the end, and someone can follow that. Because you're going to hand that to a new person, and they're going to go, where in the hell did you get this from? And you need to be able to show them that this is from here and this is from there. Not like, oh, you should have known that it was in the problem. Because new people won't know that, right? Someday you're going to be a manager, you're going to be a boss, and you're going to need to be thorough. Because someone's going to question you and go, well, where'd you get that number from? And you're going to go, well, I got it from right here. And they're going to go, I don't know how you got that. So just make sure you're a little more thorough with your units. But other than that, that was pretty much all that I had with that, okay? Anybody have any questions about anything? I will be posting the key online probably by lunchtime. Most of the people, it was on question number 9. If you missed any major points, it was on question number 9. All right? So, if you remember from, and that was a long, 3 days ago, 2 days ago? All right, anyhow, from Friday, Wednesday, because Friday was a review. See, it has been a week-ish. All right, so remember we talked about that water moves from an area of low concentration, or high concentration to low concentration, and the more negative the value, the less water there is. And so we had this water in the soil at negative 0.3 bars, which is, what do we call negative 0.3 bars? What is the term that we call that soil? Is it saturated? It's field capacity. So we're we've got this rain that came through and filled up all the pore spaces, and then gravity has now taken whatever water it will take out of this profile. So now we have our field capacity at negative 0.3 bars, and the psi outside in the air at the very top of the tree is negative 100 bars. So that water is going to move into the roots, up the xylem, and out the top of the tree through the stomata. So here we go again with our three terms for how we characterize soil water at saturation, field capacity, and permanent wilting point. And I think we left off somewhere here where we were saying that clays hold more than loams, loams hold more than sand. You can see this at the beach. And that somewhere here we are reaching permanent wilting point. And that is the combination of all of those Greek symbols and subscripts that we went over. So gravimetric, solute, matric, and pressure. So some of the easy ways to measure that, because we're not going to be in the lab measuring each one of those. There are some ways that we can measure that. One is like a very basic way, and so we take basically a 2-inch aluminum ring, the bulk density ring that I was talking about in those calculations. It has a volume of 68.17 cubic centimeters. It goes in like a core, like a drill, and but it isn't about this big, and you put it in the ground, you hammer it in, and it takes a core sample of that soil, weigh it, and then dry it, and that is the mass of the water in between mass at field capacity and mass at oven dry. But one of the easier ways that we do that is with this thing that's what we call a TDR probe. So it's looks just a probe that we stick in the ground. You hit a button. Andrew, you've used one of these before. It's super cool because you don't have to measure anything. You just stick it in the ground, hit the button, gives a reading, boom, moving on. Stick it in the ground, and moving right along. Super expensive, difficult to buy. Another way that we measure this is with a field tensiometer. Basically what it's doing is it's pulling a vacuum. So the psi in the soil causes a vacuum, and we were able to measure that based on the amount of water that's drawn out of that tube. Because remember, it moves from high content to low content. So once this becomes dry, this water will then move into that area because of that pressure. So some of the, and we actually call that KSAT. And so some of the things that are going to affect that are going to be pore size. So in a clay soil, would we have large or smaller pore size? Smaller pore size. And in the sand, we would have higher, right? That's why we put sand in our golf greens, because we need the water to drain through that system so that we're not putting in a puddle, because that's really going to mess your golf score up. Baseball fields are like that. You notice they really only cover the infield. The rest of it stays open. Football fields are built on sand substrate, so the water can move through them very quickly. Because if we built it on a clay, how many of y'all actually do golf? How many? Just Tate?
I ain't good at it.
I didn't say you had to be good at it, and Hayden. So do y'all have like really good golf courses where you're from, or you got push-up greens?
It's all pretty rough.
Okay. Right? So they have these push-up greens, and because they're using native soil, the water doesn't really flow through those greens very well. But if you go to like Augusta, the water moves through it instantly, right? Like they can pull that water out of there very quickly. The structure, so the way that it's set up. If we have maybe like a vertisol, the KSAT would be quicker because we have that big crack in there and water can move in. What we're wanting to do, and what I'm gonna start looking at trying to do in Tennessee, is planting cover crops such as tillage radish that maybe open up some of those pores and start to crack that soil a little bit and allow more water to infiltrate. So I'm gonna influence that structure, kind of frack it is what they call that, just frack it a little bit to try and get some more of that water in there. Air. air is going to influence that KSAT. Y'all might remember I talked about that I was doing an experiment where I don't think I was talking about that in this class. So I had a urinalysis cup that I had filled with 4 soil types: a sand, like a silt loam, and a silty clay loam, or whatever. It was air dried, so the only thing in the cup was soil and air. Well, I dumped 100 milliliters of water on top of it, and the air had nowhere to go. So the water was just sitting on the top because the air kind of lifted it up. There was no, like, it had reached equilibrium, so I had to dig a hole, basically poke a hole down here so that the air could come to the center and come out the top as the water infiltrated in. And then we have preferential flow, or that path of least resistance. This is that clady-like structure from our clays where that water has a longer path to travel in order to move through that soil profile. And so some of these things, and this is where I was talking about with those tillage radishes, not like we can harvest them and sell them or anything, but eventually they'll decay and they'll leave a void in that soil. And that water will be able to move in there and hold as it starts to infiltrate and percolate through that soil profile. So one of the things about soil type is water doesn't move just straight down. It has to fill those pores across first. So not only do we have that capillary action coming up and down, but that capillary action also works sideways as well. So until the pores across the top are saturated, then it will start to move down. And so in 24 hours in a sandy soil like a golf green, that water has moved 6 feet down. But in a clayey soil, it fills this zone first, and there must be more water coming down, and then it will start to fill, and then more water needs to come. So if you're gonna water a clay soil, it needs to be slow and consistent, because it needs to have that water to fill up all of those pore spaces, and then the gravity and the pressure of the water will push the rest of the water down. So we added water here and started to fill those up. We need more water to press that water down. Something to think about when you're in the field. Unsaturated flow is when we're at permanent wilting point. This is how water flows into the soil as soon as it starts to rain. Something that we're going to have here is that matrix potential, where that water is held tightly around that soil colloid, that little clay particle. All of that needs to be filled first before that water becomes available in the rest of the pores. And so something you might see in this, I'm not sure I got it on the slide, is what we call antecedent moisture or antecedent water. So there's a little bit of water left in the soil before it rains. When we have a rain, we get to field capacity, or maybe -1 bars. That's going to influence how much water actually moves into that soil. We didn't really get into the calculation, but with that bulk density calculation, I can actually determine how much water is in that soil across the whole acre. And you can use that to basically make irrigation suggestions. So you've got X hundreds of thousands of gallons, so you only need to turn the irrigation on for a day. Some of the same stuff, infiltration is the rate at which the water enters the soil. So that we're talking the top inch of soil and how water gets in there. So when I think about infiltration, I'm thinking about some military movement that is some breach of some boundary. And so in soils is, I would go ahead and use this for an example. This would probably be our layer of infiltration. The rain would hit here and infiltrate this top inch. So texture, structure, there it is, antecedent moisture content. Texture, structure, organic matter, and that antecedent moisture content. So if this is dry, and dry for a while, this little top layer, you might get what we call hydrophobic soils. Kind of like a sponge that's extremely dry. Water, it doesn't really absorb right off the bat, does it? It takes a lot of water in order to fill those pores because it's become hydrophobic. And so if we have hydrophobic soils and they're hard and we're at permanent wilting point, we get this hard rain that comes and we don't have any moisture in here, some of that water is going to infiltrate, but the rest of it will not. It'll either puddle up or it will run off. Kind of like how we talked about in soil and water conservation. So the conditions need to be just right, or else we're gonna lose that water into the ditch. And temperature. And so warm soils are gonna hold more than cold soils. That's why our gelisols don't form any soil, because y'all remember how fast the biochemical reaction increases for every 10 degrees Celsius increase in temperature? It doubles. So the biochemical reaction doubles in our warmer soils, and that's how come they're more weathered. In Brazil, in Georgia, kind of Tennessee, because those soils are old and they get a lot of rainfall. So now we have temperature and water that's making that biochemical reaction and that weathering process become more rapid, but not in vain. And finally, compaction. So that's what bulk density tells you. That if you have a very high bulk density, the mineral component of that pie chart is the most, which means the pore space is very small. So the larger the bulk density, the smaller the total pore space. And then this is just kind of showing that we will move from moist or high water content to low water content, or we will move from warm to cool. Now percolation is the movement after it makes it into the profile. So going back to our military movement, we infiltrate this soil or stronghold, and once we break that line, the rest of the troops come through, and then they go in and do all the plundering and the pillaging. Well, when the water breaks into this top little layer, remember it's going to come out some, and then it will start to move down. And so once it starts to move down, that is the percolation. So the infiltration is barely breaking into the soil profile. And that's why we want this nice, slow, steady rain. So when we had the remnants from Hurricane Ida, what's the name of that hurricane, that came through, that's ideal. It just rained for a whole day. Very slow, very consistent. And that water was able to fill all these pore spaces and then start to make its way down in the soil profile. We need more of that. Does anybody know why we need more water movement through the soil profile?
Minus the water table.
The water table. Our water tables are dropping because there's no infiltration. There's no percolation all the way down because we have these soils that are compacted or they're hydrophobic because we're running into droughts. So our soils go no rain all summer. We get something like squall line that comes by, and now we're getting the same amount of rainfall every year. That's not changing, but most of it is going to runoff because it's not making it into the soil profile, and it's not making it to the water table because we don't have that consistent rainfall pushing that water down through the B depth and down into the water table. Like, this is something y'all are gonna encounter in the next 10 years. The Ogallala Aquifer is being used up way quicker than we're replenishing it. The Mississippi River Valley, Alluvium Valley, that reservoir going quickly because we're irrigating our crops all the time because we need to grow them for food. So where are we gonna get the water from? Going back to soil and water conservation, Hannah, what are some of the things that we can do in order to conserve some of the water that's falling? Drew just kinda, don't look at me, man. What about it, Logan? What's that? What were some of the things that we talked about that we can capture rain with? Irrigation, so permeable surfaces, rain barrels, green roofs. These are going to be some things that we're going to need to implement into our systems so that we can capture some of that water because it's gonna run off. We can't get it back after that. We have to wait for it to go back into the atmosphere and fall again. So we need to start figuring out ways to capture that in ponds, rain barrels for small gardens or vertical farming, whatever it is that you're into. Like this, it's not gonna make it down there anymore. Or it'll get into the soil profile and then it'll just kind of hang out there because there's nothing else to push it back, and eventually it will go back into the atmosphere. So, something to think about in the future. How do we capture the rain? We get the same amount, yet we do not have enough to put back. This wetting front was kind of where we were talking about in that KSAP picture. So the water fell here, and then it had to spread out first and then start to move down. So we need more water to make that front move, just like a regular weather front. And that's going to be gravity and a little bit of pressure. So more water on top of it is going to force that to go down. Because as objects get heavier, gravity becomes stronger. Once we infiltrate and it starts to percolate down and we start getting near the lower parts of the A depth, that matrix potential is going to take over, and capillary action and adhesion and cohesion are going to kind of work together to pull that water down some. But if there's no water above it, it'll start to rise back up because the pressure outside is negative 100 bars. And water moves from areas of high content to low content. So your water is going to fluctuate in your soil profile. Again, this is what we call the wetting front, right here. And then we need more water, and then we have a bigger wetting front, and finally our large kind of push towards the bottom of our profile. The way that this is where kind of taking 12-inch samples and knowing what is underneath your sand is also going to influence how well your water drains. So not just knowing the top 6 inches, but also maybe the bottom 6, like the bottom 12, maybe 2 feet down, so you can understand how that water is going to move. Is there something underneath that's stopping that water? Is there something underneath, like sand, that's forcing that water to flow out quicker? Soil depth and layering, that's going to be that stratification. Maybe we have an impermeable layer. Those rooting characteristics, so that's why we want to use tillage radishes, because it'll break up that hard pan that we may have from driving our tractors, or from no-till and not tilling enough to break those pans up. And this is going to be the last one for this part of it. So we have 3 routes of water into the soil, into our roots. So capillary action, that xylem, the xylem in that plant is much smaller or about the diameter of the micropores in the soil. So it will start to move towards, once the water makes it to that plant, it will start to move up the plant because of the capillary action. Root to soil contact. I know these are kind of no-brainers. Obviously, roots need to at least come in contact with some water. So when those roots shrink, so we have a rain and the plant is turgid, it has water in all of its cells and it's kind of swole out a little bit. As it starts to get to permanent wilting point, we lose water in the plant from evaporation, evapotranspiration out the stomata. That root will start to shrink just a little bit, just enough. And if we don't have any root to soil contact, that plant is actually breathing in air. We call that an embolism. And so if the plants don't have enough water to pull into their system, they're pulling in air. And that is going to end up killing the plant. So we need to make sure that we're establishing that contact. And then finally, root extension. And so when we start to grow crops in the beginning of the year, we might get them enough water to get them established, and then we might water for a long time and try and get that water deep down in the soil, and then we'll cut the water off, and we'll force that plant to grow towards that water, because it will, that root will follow that water down because it needs it, and so it will start to grow even harder and even better and infiltrate and start mining that soil so that it can get to the water that's way down, that's like a foot down. Because it can pull some of that water up, but it needs to be way down there. And so we'll do that so that we can strengthen our plants, kind of put them through a little test, stress them a little bit, so that we can, when we do get another rain or we do put another irrigation on it, they'll be able to take up that water better. And so this is just a cross section where we have, here we have our macro and micropores, our xylem, and our phloem. And so water moves up these. So as we start to take up more of this water, now we don't have as much root to soil contact because this root has shrunken. And so this area right here filled with air. And when that plant's looking for water and sucking for air, that causes a problem. And so that water kind of dies out. Also, what will happen is, because the potential is greater out here, the water will leave the plant and try to fill this matrix potential. So we're kind of in the balance back and forth between how we manage our water and just understanding that this thing happens. That's why in greenhouses we have to water plants all the time, because that root to soil contact isn't there. There's not enough water and our plants die. And then we can't get them back once it's past permanent wilting point. There's a reason they named it that. It can't get any water back in. So just a kind of quick brief introduction about water and why it's important in the soil and how it interacts. All right, that's all I got for today. Y'all enjoy your lunch. Oh, no class on Wednesday. Someone asked about if we were going to have class before the test, and that's a no. But I will send out a thing for you to sign up to take your test during the lab.